Hello, everyone. Welcome to the IEEE Communication Society podcast series, and this is episode 24. And I'm your usual host, Professor Aryan Kaushik, Associated as Senior Editor with IEEE CTN. Today in this podcast, we have two esteemed guests. So they are with the industry. So we have, first of all, Dr. Doohwan Lee from NTT in Japan. He's a senior distinguished researcher. And then we got Dr. Hirofumi Sasaki as well. He's also a distinguished researcher with NTT Japan. So first of all, welcome, gentlemen.
Thank you very much for inviting us.
Thank you for joining us.
Pleasure to come here.
Thank you, guys. So today's podcast topic, Doohwan and Hirofumi, we wanted to touch on the topic of electromagnetic signal and information theory, right? So as we see, this is a new initiative that we got with IEEE Communication Society, right? So where we are having a technical working group. So I'm involved as chair, Doohwan, you're as the industry co-chair, and Hirofumi is yet to be joining that group as well. So basically the concept of ESIT that we see is kind of merging three different fields all together, right? So you get electromagnetic wave theory, you got information theory and signal processing all together, right? So electromagnetic wave theory is like, let's say, your Maxwell equations, your physics equations, right, for the propagation that we have. Then they are difficult to solve, so we make them easier to solve by using information theory. We use some probabilistic models and things like that. And then we use signal processing to basically make it more efficient solution at the end of the sort of algorithms or compressed sensing we use, or let's say we use something from the convex optimization to make it more efficient. So that is the basic concept, right? So in this one, we have many different topics, right? So let's say multi-shape radio, so where you guys work on, like you're experts on that, right? So I wanted to ask you guys, in the context of ESIT, where does multi-shape radio stand? And what do you guys want to kind of talk about in the podcast that you're working on recently, the latest work that you're doing? If you would like to touch on that, Doohwan.
Okay, we have, thank you for the introduction. We have researched a lot about information theory based on Shannon communication capacity theory.
Yeah.
If you see the Shannon theory is a beautiful theory. So everything works well, still works well, but there is still a lot of approximation. So in 6G and beyond, we want to do more than assumption based on Shannon theory. For example, we want to use spherical wave. We want to set the antenna antenna allocation less than half lambda, and we have to consider more near field channel effect. In the case, Shannon theory is based on far field approximation, so we want to do more accurate model. So there is a lot of academic researchers working on ESIT to find the exact channel capacity and degree of freedom. But in terms of industry research, so we have a bit different. We are doing the similar one, but a bit different thing is that we want to pursue more experimental study and more practical study to be the product. So our concept is that the thing is Shannon theory and ESIT. ESIT researchers in the academia try to find the accurate solution or more proper solution which combines information theory and Maxwell electromagnetic wave theory.
Yes.
But in my concept, we want to add some kind of practical aspect. For example, Shannon theory, they based on the exact SNR, which means that perfect DSP, digital signal processing. Everything is done in the receiver side, so channel estimation on everything is done. We have a final SNR, then we consider the capacity based on bandwidth and SNR. But ESIT academic researchers, they incorporate Maxwell theory to the capacity analysis framework, but they also based on the perfect DSP capacity. But our approach is that actually in the real system, for example, we'll talk about later, in the subthrust band, the DSP has a limitation. We cannot assume in practically the perfect digital signal processing in both two ways because the bandwidth is too large, so we have to consume a lot of power consumption.
There will be some distortions as well.
Distortion. At the same time, at the same time, we want to share some digital signal processing burden in the digital domain and analog domain and wave domain. So we want to add some constraint. We cannot do the digital signal processing. We want to do some thing more in the analog domain or electromagnetic wave domain. In the 5G, in the hybrid analog and digital architecture concept, they try to divide the signal processing in the digital domain and analog domain. But for the 6G, in cooperative with ESIT, we want to do more in the EM wave domain. So we try to exploit, this is the multi-shape theory, multi-shape radio. We want to try the more possibilities of EM waves that was not exploited yet. So for example, we'll explain later, orbital angular momentum, Airy beams and Bessel beam, which is different from the conventional Gaussian beam, but it has a large potential. We can use that in the various way, then we don't need to spend a lot of power for the DSP.
Yeah, so we're pushing, let's say, the limits of Shannon capacity, right? We're trying to achieve more things than what we were able to do until now. So you mentioned about the far field sort of beamforming and, far field sort of communications that we were aiming for. Now we are moving more towards the near field side.
Sure.
But do you think that this can be a hybrid approach as well, that you have far field, near field together with multi-shape radio?
Yeah, of course. Actually, we have to use we don't need to strictly divide far field and near field. We can use both.
Depending on the application that we have.
But for we have some example of multi-shape radio, like using orbital angular momentum multiplexing and Airy beams and Bessel beams and the other arbitrary beams. Some beams can be only operated in near field because their freedom is we can exploit that they are characteristic in the near field. But some beams we can use that in the far field. So depends on the characteristic of beam, we can use that in the near field. We can even use the near field and the far field.
Yes, correct. And also you mentioned about OAM, right? So I wanted to ask Hirofumi about OAM. So you are working on that technology. So where does it fit into the context of ESIT, and what kind of benefits we can get from OAM? Hirofumi.
Yeah, thank you for asking about OAM. So OAM, orbital angular momentum, is one of the physical property of electromagnetic waves, and it has a rotating phase front. It's often called twisted wave. Yeah. So it's also kind of a wavefront engineering or wavefront shaping, kind of that. Yeah, beam manipulation, kind of that. Yeah, right. So, and we can use the multiple OAM mode for the multiplexing, signal multiplexing, because they form in the orthogonal basis set. So for the rotating direction. Yeah. So and point-to-point communication, usually, typically we can send as one signal, because point-to-point, there's no multipath or just a line of sight. There's one path. But if we use the orbital angular momentum or kind of such multi-shape radio technologies based on the engineering, we can multiplex signals using the orthogonal basis set. And so the orthogonal states of OAM is maintained during propagation. So only the fixed processing is necessary to generate separate OAM beams, giving just a rotating phase front, and we can coaxially multiplex the signals using OAM. So we can use the analog devices to generate separate OAM beams. That is very good, suitable for the future, higher frequency communication system like terahertz communication and so on.
So how do you combine this with terahertz? So what are the benefits that we get with terahertz, not with our microwave spectrum, or let's say we were talking about centimeter wave as well, right? With 6G, probably centimeter wave is really the key enabler, right? So how does OAM fit with like high frequency modeling? And can it operate also at low frequencies as well as we use in our infrastructure currently?
So, the near field can be extended if we use a higher frequency one. It's depend on the size of aperture, antenna aperture, and also linearly proportional to the frequency. So higher frequency is better to use a near field and to multiplex or any other, wavefront engineering kind of multi-shape radio. Higher is better. And also they have very wide bandwidth, more than 10 gigahertz and so on. So we can increase the capacity very well. In the
but Hirofumi and Doohwan, there may be a bit of challenge because, as I was mentioning earlier, because we are not considering terahertz just right away for 6G systems like what we are going to implement, right? So we are thinking of maybe low to mid band spectrum, basically, right? We are not thinking of sub-terahertz, terahertz bands. Okay, we say that sub-terahertz can be a complementary spectrum, so we don't need to use it everywhere, but wherever in some geographical locations we may require it, right? So we are, of course, evolving towards high-frequency spectrum to get the high capacity and, have the large bandwidth. And, there are some other challenges with high frequency, right? But the thing is, in the current scenario, we are focusing more on the low to mid-band spectrum. So what do you have to say about that?
Yeah.
Like with OAM,
Sure. Actually, in industry, we are doing long-term research. So our research unit has a short-term future, near future research, and long-term future research.
So you're thinking like many years,
Yeah,
maybe beyond 6G.
As we mentioned, sub-terahertz is not included only in the day 1 6G, the first 6G, but day 0 6G, day 1 6G, but the day 2 6G or maybe beyond
maybe 6G advanced.
Yeah, 6G advanced, maybe, I'm not sure, beyond 6G or 6G advanced or 7G. Sub-terahertz will be, introduced again, we believe that. So as a long-term research unit, we are still have believed that there is potential and there's great has a room and great opportunity. We can use sub-terahertz band and higher frequency band. So even though many people are working on the mid-band for the day 1 6G, that's true. So that is important. But after that, we believe that sub-terahertz will be necessary.
And how about airy beams, Bessel beams, and this kind of concepts?
Airy beam is quite interesting. So as I mentioned in the beginning, we use unused electromagnetic wave characteristic, EM wave characteristic. For example, airy beam has very unique characteristic. It's a side lobe. Normally, side lobe causes interference, but side lobe distributes asymmetrically. Normally, the traditional Gaussian beam has a side lobe is symmetric. So everywhere there is a side lobe, which means that everywhere it causes interference. But in airy beam case, the side lobe distributes only some part. There is a side lobe full region. So we can use airy beam to generate multiple streams without interference region. So we can transmit multiple signals without interference using airy beams.
Mm-hmm. That sounds interesting.
Yes.
Hirofumi, do you also work around these ideas or more on the OAM side, basically, your work?
Lower frequency one. But I have the same opinion for that. I mean, we focus on the very future works on day 2, day 3, 67 channel there. Yeah, so I'm sorry, I have a same opinion.
Yes.
Yeah, we want to use much higher frequency one to increase the capacity, or because in urban areas sometimes and my cell phone doesn't work in Tokyo urban area and so on. So the resource is very much limited now. Yeah, of course we extended sub 6G or millimeter wave and so on, but we want to use much higher frequency band and even the optical FSO and so on.
FSO as well.
So we want to be pioneer.
Yeah, so I think this leads to me like another sort of intriguing thought. So let's say when you basically want to use ESIT, so we look for some synergies with some other sort of technologies, right? So let's say with non-terrestrial networks, I think ESIT can have very good synergy, right? So when you're basically trying to hit some use cases, or let's say in public safety or maybe mission critical services, some disaster management scenarios, right? So there basically you can have, our technologies like reconfigurable intelligence surfaces or holographic MIMO or OAM as well, and utilizing maybe Bessel beams, airy beams, right? Then basically you're trying to integrate the non-terrestrial entities with the terrestrial network, synergizing with the concept of ESIT, right? So basically you probably try to achieve better capacity, you try to achieve lower latency with kind of covering larger distances and so on. So ESIT has very good concept there. And again, as Hirofumi mentioned, with the optical side as well. So let's say with a drone that is, kind of like swarm of UAVs we got, right? So they have some battery limited capabilities. So how do we make sure that they're charged all the time, right? So probably we need to use some optical sort of technology, maybe we kind of hit a laser there and kind of charge it from maybe some other like distance, maybe some other control unit or something that basically keeps it going, the swarm of UAVs, right? So in this case, optical also seems to be kind of amalgamated with the techniques of communication. So this leads to me like, applications, first of all, use cases, synergizing ESIT and the concepts we have been talking about with other technologies like NTN for, better use cases. Then at the same time, you combine this with technologies like photonics, like optical sort of communication. So this is really like a wide sort of variety of techniques we are trying to combine. So I wanted to ask you guys, you also touch on, let's say, the signal processing that is assisted by photonics or with, sort of optical principles. So what do you have to think about, what do you have to kind of share with us in this area where we use photonics assisted, especially for, let's say, RF signal processing that we talk about, or even in the case of, wave domain signal processing where we explore the concepts of ESIT quite much. So what do you have to say about that?
So I'll give a brief answer. He's an expert. I'll give a brief answer. So as you mentioned, photonics communication, combining between wireless communication and photonics is very important and emerging. And so like you mentioned, we can use that as new application like NTN. So that is very good example. But our group is working on the photonics as a kind of substitute or to overcome some kind of bottleneck of electric signal processing. For example, photonics, we can increase the number of RF chain that is more than maybe 10 times more than electronic when we use electronic.
But this doesn't lead to high complexity, Doohwan? Like if you really increase...
Yeah, that is good keyword, complexity. If we use photonics, we can, excessively decrease the complexity when we use photonics. So,
and how do we do that?
So then maybe he can answer.
Complexity, right? Yeah. But also it's a little bit different story. But so we can use the wavelengths resources very much compared to the RF. So we can use wavelengths, so many WDM wavelengths as a degree of freedom for the signal processing compared to RF signal processing. So for example, in terms of the RF beamforming, so we can use multiple WDM signals and then give some kind of matrix multiplication, right? Yeah. For the to make a beams using the analog photonic circuit and to true time delay based something or phase shifting delay something. So we can control the signal's direction easily in the photonics region, and the wavelengths become very short compared to the RF. So the components become very small, and also power consumption become very low because almost no loss in the fibers or photonic circuit. It's natural things. So it is a very good approach, I think, to do signal processing, analog signal processing during any photonics region. And for example, not only RF beamforming, but also some kind of modulation, demodulation, coding, everything.
Or on the system side as well.
It's called optical computing or the kind of that, or neural networks, optical neural networks there. So anything, I think I wanted to do that. Everything will be done in the optical domain.
Right. This is interesting, guys. This is actually very futuristic. I mean, the way you explained it.
But maybe it's so hot topic. Listen to it.
Perfect. So before we actually conclude our podcast, Doohwan and Hirofumi, so do you guys want to touch on something like the next steps on these technologies? What are you thinking that will be actually standardized? And that will be actually also put forward for beyond 6G, right? So let's say we are talking something about 7G. So from our perspective, for example, it can be quantum communications, quantum AI, combined with, sort of machine learning algorithms and so on. So that seems like sort of going beyond 6G. Of course, we have to realize the technologies that we are talking about, like integration of sensing and communication, non-terrestrial networks, not just using it for emergency SOS, but going beyond, like to support the, use cases like public safety and so on. And also utilizing AI with, communication and use those principles to realize communication and using communication principles and fundamentals for AI as well, right? So what do you guys think from your perspective, from your industry side? We want to know the industry point of view, right? Will be the sort of future steps, will be the next steps, going forward into 6G and beyond 6G, into perhaps 6G advanced and 7G and perhaps even beyond. What do you guys think?
Before I ask your question, there's a really good question. In my company, we have research unit of our long-term future research unit and standardization unit and development unit. So because we belong to the long-term future research. So I will not touch on standardization. Standardization is done by other groups, but that is very important. Actually, development is also very important. For in our research side, he's will be expert of optical communication, and in my case, I want to find the extreme opportunity of the electromagnetic wave processing. So recently, using intelligent meta surface, like Professor Alenjo, he was also on the podcast before. So I want to find the extreme opportunity of possibility how we can use EM wave, and we can use the signal processing not only in the analog domain, in the EM wave domain. So we want to do that using stacked RIS or stacked intelligent meta surface.
That is a new concept coming up.
We want to do signal processing in the wave domain.
Increasing the degrees of freedom, so you use multiple layers of the meta surface instead of just using one. Hirofumi, any thoughts?
So a little different point of view, but I'm working on the photonics technology based LF beamforming or signal processing, and also some kind of quantum computing or in the future, not so far, but in the future. So we need to converge so many technologies in the 6G and 7G. The convergence is very important, I think. And for example, I talked about something, beamforming or some codebook based beamforming, like an array beam or vessel beam. But how to manage the beams, that is also very important things, kind of beam management and AI based or quantum computing based optimization and anything. So I wanted to reveal the use quantum computing to such kind of optimization.
Kind of mixing up different technologies and using quantum too. This is what we are thinking as well in the physical layer.
At the time sensing is very important, So a little bit different from channel estimation, but also the position detection or some kind of any other things is necessary to choose the beams or to form the orbital waves, to choose the code. So I want to implement some AI or quantum computing to the ISAC scenarios in the terahertz communication. So that is my future perspective.
Perfect. This is amazing, actually. This is very futuristic. You guys talked about the things, right? Okay, so just before we conclude, other point I wanted to mention was that we deliver a lot of tutorials together, right? So ICCs, Globecoms, we have industry panels. So for the audience who are interested to follow on the topic, so if you're attending these conferences, so we are now going to ICC 2026.
Yes.
Tomorrow we have a tutorial as well. So we are recording just one day before ICC 2026. So please kind of attend our tutorials that Doohwan, Hirofumi, and myself, and sometimes with Marco as well, we kind of present these. We talk about these ideas, these topics, and so on. So with this, thank you so much, guys, for joining us, and it was great to chat with you. And hopefully, maybe in a year or 2 years, we catch up again and we see where we are with the technologies we talked about. Thank you so much.
Sure, thank you very much.
Thank you.
Cheers, thank you.